All right. Hearing no other traffic for tonight's business meeting, we'll go ahead and adjourn that and turn it over to Scott for the presentation.
Okay, can I just go
Let's,
ahead and hit share my screen, or you
yep,
have to
should
do
be all
that first?
good. If you need anything, let me know.
Okay, I'm turning on share screen now. Let's see if it works. Can you all see my screen?
Uh, yep, just came up.
Yeah, okay, now it's on. Okay, let me get the presentation underway here. I actually had unfortunately, I can't do it on this particular computer, but I have um, what do you call it? Well, basically, there's an ability to draw PowerPoint slides. I guess maybe a couple of you might know that, but I didn't know that till recently. So I have a stylus style mouse, and let me see, where am I here? And yeah, let's start from the start. And I was going to use that as part of the presentation, like, actually write stuff on the slides in real time. But on this computer, I can't get that system to work. And I was on this is a Mac that I'm on right now. And then the PC I got in the same room was working. But the problem is the microphone didn't, I couldn't get audio. So, or at least my voice onto the meeting. So I had to come back to this computer, so I won't be able to draw on the slides, but I guess that's okay. I don't think I'll really need to. But anyway, so I'm going to be talking about SWR today. Not super long. I think this will probably take about a half an hour, unless you have questions. If you're so interested. Mike Shelby asked me to do this because he's away this month, and he suggested this topic because I don't know how many people, well, maybe none of you guys do, listen to the TechNet or technical discussion on WA7AB repeater that's up in Silverton. And it has great coverage all over, pretty much from into Washington all the way down to Roseburg, or well, not really Roseburg, but Eugene anyway. And so a lot of hams are on that TechNet. If you don't know about it, it's just a weekday discussion net that's on 10 o'clock in the morning to 11 o'clock in the morning, Monday through Friday. And there's a lot of good stuff that gets discussed. If you have the time, that time in the morning, it's the 529 repeater, and there's no tone involved. I would suggest listening and maybe participating because it's a really good net. And some days the discussion gets very, very lively, and we have a lot of very knowledgeable people on that net, actually. I'm a net control 1 day a week. I'm on Tuesdays, so tomorrow I'll be on as net control. But anyway, so Mike Shelby apparently listens to it. He never checks into it, but he told me he listens to it all the time. And he heard me just talk about SWR one day. And so he thought that would be a good topic to talk about here. So I said, okay, I can throw something together and hopefully have it make some sense. I think everybody pretty much knows what SWR is, but I'll just go over some of the basics and some of the non-basics as well. And then just to, maybe generate some interest or questions, and also just go ahead and give a kind of a review on all this stuff. So let me continue here. So it's all based on standing waves. Okay, so I found this animation on Wikipedia, and I might have shown this in my some of my classes, but I'm not sure about that. Anyway, you have in front of you you have three waves that are going on there, three sine waves, and there's a forward moving sine wave that would be the blue one going to the right on your screen, and then there's a reflected wave that will come back going to the left. That's the red one, and where they cross paths and destructively and constructively and destructively interfere, they're going to create the standing wave pattern. So the black sine wave is the standing wave. And as you see, it's standing in one place relative to the other two waves, but it's going up and down. So it is oscillating. And the other two waves are called traveling waves. Okay. So the blue wave is say, the forward wave. We can also call that the incident wave because that's basically going to come from a generator of some sort, like a transmitter, and go to a load. And the thing it's traveling on is a transmission line. Okay. So a piece of coax. And then if the load is not matched in impedance to the transmission line impedance, then there'll be a reflection of some of that power. And that will be the red sine wave going in the opposite direction. All right. And so again, as they cross each other, they're sliding past each other, and they're going to create regions of constructive and destructive interference that are going to have, create the standing wave. And the standing wave will have the same frequency and wavelength and all that as the other two waves there, because it's really, the initial wave is of course the incident wave or the forward wave in blue, and then that's going to get reflected, or some of it will get reflected into the red wave going backwards. So, the characteristics of the wave are the same. It's going to have the same, well, it won't have the same amplitude necessarily, but it certainly will have the same frequency. Okay, and the phase there could be a phase difference as well, and we'll talk about that. So that's the basics of what SWR is all about. So, standing wave ratio (SWR) is going to be a ratio of the let's say a maximum voltage to a minimum voltage along the line. Now, so what we're looking at here, you could consider voltage waves. All right, so there will also be a current wave, and the voltage and current waves will probably be in phase, okay, as they travel down together down the transmission line. And when they get reflected, there will be a out of phase effect. We'll talk about the difference, if the voltage is in phase, say the reflected voltage wave is in phase with the incident voltage wave, and the current wave could be 180 degrees out of phase, or vice versa, that kind of thing, and what conditions cause all that. Okay, so are any questions, rattling around in your mind so far? Nothing? Okay, I'll move on. Okay, now let's get in a little bit of math here. Okay, so basically, we're going to talk about this. Oh, too bad I don't have. Can you see my cursor? Can you guys see my cursor as a pointer?
Yeah, we can see it.
You can't see it? Wait,
Yeah,
I
it's
think I
small,
can
but we can
actually.
see it.
Yeah, I think actually I can draw on these slides too, by the way. I can, yeah, you can go down to the bottom left here and you can see that these little icons are available. And so you can actually select the pen icon, and you can if you guys do a presentation to anybody, just keep this in mind. So you can have your pen as a cursor as a highlighter, a pen, or a laser pointer. So the pen will actually allow you to draw stuff, things like that. And of course, laser, oops, I didn't mean that to happen. Um, and I'll just use it as a laser pointer to make it a little bit easier to see stuff. Okay, so this quantity rho here, well, that's called the reflection coefficient. Sometimes it's the quantity gamma as well. So what it is the reflection coefficient is the, uh, did I get this wrong? No, this is correct. The reverse, it would be say the V stands for the voltage. So this would be corresponding to a voltage wave. It could also be a current wave, but let's just work with voltage for now. So the maximum of the current wave, let's say in the reverse direction divided by the maximum of the current wave in the forward direction, will give you the reflection coefficient. Since the reverse wave is not going to be bigger in voltage usually than the forward wave, the maximum value for a rho here is 1, and it can go down to 0. So a rho of 0 means no reflection, and a rho of equal 1, it means total reflection. So in the case of 1, VR is equal to VF. So that means the reverse wave is the same amplitude as the forward wave, and that means that the wave is being totally reflected. 0 means that there's no reflection. VR would be 0, and therefore there would be no reflected wave. Okay, so there's, you can derive formulas where you can relate SWR to rho. Again, the rho is a reflection coefficient. So SWR, which we are pretty much familiar with, if you get an SWR value, let's say from your antenna analyzer, and you plug that into this formula, you can compute rho. Okay, if you need to get, for whatever reason, the reflection coefficient, and vice versa. If you know the reflection coefficient, you can plug that number into this formula down here and get the SWR. So they are both related to each other. So basically what's going on is this. You've got a current wave traveling down your coax or your transmission line, and you also have a voltage wave, okay? And the two, well, these aren't coordinated, but basically On the left here, you can imagine there's a generator. In fact, let me see if I can even draw one in. If I just convert this to a pen. So I've got a, let's see if this will work. Yeah, here's my generator. Okay, so it's putting out this wave and and the generator, I got one over here. Okay, sorry for the crude drawing, but I think you get the idea. So these are basically the same generator. And once, so they're putting out both voltage and current as a wave. And right here, this line and the dash line over here, these are barriers. So let's assume we got a piece of coax that the waves are traveling down. And at the end of the coax, it's just not terminated. Let's just say it's an open circuit. It's just you got a piece of coax connected to your transmitter or your transceiver, and there's nothing attached to the other end. You forgot to connect it to the antenna or anything else for that matter. So there's no load there. All right, just an open-ended piece of coax. So what's going to happen? Well, okay, first off, let's look at the voltage wave on the right. You see that the voltage wave will go back and forth, and when it hits the barrier, it increases in amplitude and then starts coming back for the generator over here. Okay, so it hits the wall, hits the termination, it almost doubles in amplitude. You can see that. I mean, if we can measure it, it would be probably 2 times. And then but when it travels back, it's the same amplitude as the forward wave. Okay. Now on the current side over here, you'll notice that what happens is the current wave will hit the wall and it will invert itself and travel down the coax, 180 degrees out of phase than the incident wave over here. This is the current wave now. Okay. So this is what happens at the end of a open-ended piece of coax. The reason why this happens is, well, first off, we know that at an open end, the current has to go to zero, correct? Because the current can't travel continue to the right if the coax isn't connected to anything. So that means the current has to drop to zero. Okay, but what happens is the wave doesn't just go to zero, it inverts itself. So it is at 180 degrees out of phase. The reverse wave, that is 180 degrees out of phase with the forward wave. So when the two waves if I could freeze this, thing, I could show you right when the wave is at the termination here. You've got the incident wave is up and the reverse wave is down, and they're going to basically cancel each other out. Okay, so effectively you've got zero current here at this line or this termination of the coax. So that makes sense? Because current has to be zero there. So if you look at current as this wave, the only way that's going to happen is if the wave reverses itself and also inverts itself, besides not just reverses its direction, but inverts its phase. So it's 180 degrees out of phase with the incident wave. Therefore, right at the border, or I should say right at the termination, you get zero current. Okay, so that makes sense physically, correct? Now, for the voltage side, what happens is the voltage is going to double effectively, but only right here at the termination. Okay, so but what's going to happen is it will not invert its phase. The phase will remain the same as the incident wave, so it stays the constant. Now, that's one extreme. Okay, and are there any questions so far? I don't want to go too fast. All right. Now, if we reverse this, let's suppose I call this the current wave. Well, let me back up. Let's suppose now instead of an open circuit, I've got a short circuit. So I got my coax, and I really did a bad job putting on my connector. My PL239 connector is shorted. Okay, which many of us have done, I'm sure, if we've done our own coax connectors. So you shorted out your coax connector, and you didn't bother to check it with a multimeter before you actually started using that piece of coax, and you just assumed it was okay, but it wasn't. Okay, you actually had a shorted connector on the other end there. So now what happens if it's shorted? So let's reverse this, or I should say, let's swap these. this is now the volt where I can't, well, I guess I can. Hang on. I guess I can, yeah. This is now current, and the current is now voltage. Okay. So now instead of the voltage wave um, doubling, it's the current wave that's going to double. And when it hits the short circuit, because at the short circuit, the current can flow through, but what happens to the voltage at the short circuit? Is there voltage at a short circuit? No, there's a short circuit by definition is zero voltage. So now instead of the current wave coming to the termination and inverting its phase, it's the voltage wave that does that. Okay, so the voltage has to go to zero at the short circuit. So that's why this happens. All right, but the current is not, restricted to go to zero. So it's going to do the same kind of thing. It's like a barrier here. The short circuit acts as a barrier, and it will reflect the current wave back. And so you get this, you get the current wave and the voltage wave behaving in this manner. All right, so those are the two extremes of reflections, short circuit and open circuit. So what about stuff in between? Well, let me move on here. Okay, so stuff in between, where now you don't have either a short circuit or a open circuit, and now some of the power or energy anyway. I won't call this power yet. Let's call this a voltage wave, which is what we're representing here. The voltage wave continues past the this line here, which represents, oh, I forgot to draw this in, but this is going to represent two impedances. You're going to have a Z, this impedance 2 over here, and this is going to be impedance 1 over here. Okay? So at this barrier or line here, whatever you want to call it, boundary, you're going to get an impedance change. All right. If I go back to the previous slides, I can say that, yeah, the beyond on the right side of the termination where there was either a short or an open, the impedance was 0. And on the left side of it, it would say the coax line characteristic impedance, say 50 ohms. And suddenly comes, if you have a short circuit or open circuit, suddenly, the 50 ohms disappears and now it's infinite ohms. Or at the short circuit, it's 0 ohms, I guess you can say. Okay, so here we have something in between. So we've got Z2 is, going to be some relationship to Z1. In the case here, we see that, okay, let's trace this. Here comes a voltage wave. It hits the impedance barrier, and notice it continues past to the right of the impedance barrier, but it's smaller. This wave here is smaller on the left is smaller than on the right. So you can say that the voltage is less, okay? So what does that mean? Since impedance is equal to voltage over current, okay, so if V2, let's say V2, and I won't call I'll just call it current. And this is for Z1, it's going to be V1 divided by I. Of course, you can call it an I1 and an I2 if you want, but I'm going to leave that open for now. So V1 and V2. So V2 is smaller than V1. And therefore, the impedance Z2 has to be smaller than Z1. Okay? Because the relationship between voltage and current for impedance, if V2 is smaller and I stays, say, the same, well, I could change as well. We don't know what's going on with I yet. But anyways, just assume that I1 and I2 are equal. I'll just call this I1 for now. I2, they're equal to each other. So Z2 has to be smaller than Z1. Okay. If I might get a situation that I get a bigger voltage wave than the incident voltage wave over here. This is the transmitted wave, by the way. So the transmitted voltage is actually bigger than the incident voltage. That would imply that you have a bigger impedance here. And then, of course, the currents would change because the impedance, if Z2 is bigger than Z1, then you have to have less current crossing this barrier, and you have to have bigger voltage, less current than V1 and I1, okay, to make the impedances work out. So you're reflecting, okay, in the case here, we're reflecting. Okay, let's go back to what we're actually seeing. So since V2 is smaller than V1, then the reflected wave, we'll talk about that now. That's the reflected wave here. The reflected voltage is going to be opposite in sign, I should say opposite in phase. So some of the reflected voltage cancels some of the incident voltage in order for this transmitted voltage to be, smaller, a smaller value than the incident voltage. Does that make sense? So I'm reflecting back some of the voltage wave here to get rid of it. So I have less voltage wave going through and being transmitted, but the reflected voltage wave is actually inverted. So that means the incident voltage and the reflective voltage, you subtract the reflective voltage from the incident voltage, or I should say maybe you add them together, but the reflected voltage is negative. So therefore it's effectively subtracted. And then therefore the reflected wave, also reflected voltage wave is actually small as well. Okay. So that's really what's happening in our transmission lines. And you can also consider this over here, the antenna. So this is a voltage wave going onto the antenna from the coax. Okay, if the antenna impedance is smaller than the coax impedance, let's say you're matched or you've got a 50 ohm line connected to a 25 ohm antenna input impedance or 30 something ohm antenna impedance. So there you've got Z2 smaller than Z1, and therefore you get this effect. So you're reflecting some of that voltage back down the transmission line back to the transmitter. And then the current, I don't have a picture for the current, but the current's going to do something probably in the reverse way. Since the current maybe will increase going here, we have to sort of take away, well, the incident current coming to the barrier will continue through in any case. And then the voltage wave will probably be adjusted such that the ratio between the two will give you Z2. Okay, any questions on that so far? Okay, and what's going on here, I just wanted to point out here we've got reflection coefficient. So over here, again, it's going to be the forward divided by the reverse voltages, not anything to do with the transmitted voltage. And it doesn't have anything to do with the phase. We don't see phase here. It's just whatever the magnitudes are. Okay, so let me move on from there. Okay, so this looks a little complex, but it's really not if you look at it. What this is basically is what the standing wave patterns look like on your coax line. So I'm relating. So what they do in this graph, and I just pull these things off, off the internet. I don't make these up or anything like that. But we started off here with the green. Sorry, with the all right, what do we got here? This axis here is just basically the distance along your coax or your transmission line, and this axis here would be the voltage, maximum voltage to the minimum voltage ratio, as far as I can tell. Okay, and so we go from what they do is they draw these curves out depending on the reflection coefficient, and again, the reflection coefficient is related to the SWR through this equation here. Okay, so or this equation here. So what I did was I put on the upper right, I'm sorry, on the right side of the slide, I put the relationship between SWR and reflection coefficients. So reflection coefficient, start off with reflection coefficient equals 0, meaning no reflection at all, meaning you have a perfectly matched load to the transmission line. Basically what they call get a flat line. There's no standing waves at all. Okay, because the traveling waves, which represent the forward and reverse waves, or actually there's no reverse wave. It's just one traveling wave will be a forward wave, which feeds right into the load and is absorbed. Okay, it's either burned up as heat or it's radiated. Okay, in the case of an antenna, you want all that power to be radiated. So we can just say that the power is absorbed by the antenna and then gets radiated out. So that's the case where you have a perfectly matched system. There's no reflection at all. Okay. Now, we move up the graph, the series of curves here. And what you're seeing is, like say, when you get a reflection coefficient of 0.25, which means that Okay, it's not power. This is in terms of voltage or current. 25% of the current or voltage is being reflected. I'll get into power in a bit here. But this is a reflection coefficient 25% of the voltage, let's say. So that um, okay, and then okay, let me jump to this curve here. Rho is equal to zero point 0.5, so that's 50% of the voltage is being reflected. Okay, so that would correspond to SWR if you look over here on the right of 2. Okay, as an example. All right, and the next the curve in orange would be 75%. That would actually correspond to a curve of somewhere in between 3 and infinity, actually. I forget what the number is. 1, when you get a reflection coefficient of 1, that's 100% reflection. And that means you get it down here, infinite SWR. Okay. So we all know that because when we have a short circuit or a open circuit, like you have your coax connected to your rig or to your antenna analyzer, and you measure the SWR, and it's all the way to infinity. Well, that and you have nothing connected to the other end of the coax. Well, then you know that you have an open circuit, and that's why you're getting a reflection coefficient. I should say an infinite SWR, which would correspond to 100% reflection. Okay, but there's stuff in between. So let's look at the green curve here. Okay, so for instance, if I have a reflection coefficient of 0.25, and I didn't do the calculation, but I think that might be, isn't that 3? Or maybe 4. That might be 4. SWR 4, that is. Okay, so no, no, maybe not quite. No, 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 not quite. I'm sorry. Forget about that. But just look at the undulation here. Okay, this way the green wave is oscillating between voltage a ratio. Okay, or I should say maybe just the voltage on the line. Okay, let's say that this is just the voltage on the line. Okay, and they're measuring point to point along the transmission line. And over here at the beginning of the line, you get 1.25 um, I don't know, volts, let's say. And then, pi over 2, um, about 180 degrees later, then it drops down to 0.75, all right, volts. And then you continue along and you're measuring all these things, and it reaches the maximum again at 1.25. So you say that, okay, the ratio is 1.25 to 0.75. This is the voltage maximum here. The voltage minimum is 0.75. You take that ratio and you should get the SWR. Okay. So does anybody want to give that number? Yeah, 1.5 divided by 0.75. Well, all right. I won't put you on the spot. All right. Over here, blue line or purple line, you get a maximum of 1.5 and a minimum of zero point 0.5. Okay, that's an easy one. So if I take that ratio, 1.5 to zero point 0.5, okay, that 1.5 is the maximum, voltage maximum, 0.5 is the voltage minimum. Well, that's the ratio is 3. Okay, so okay. So let me see, is that correct? Oh, because what we should see is, yeah, that's the ratio there. Yeah, 3 and then 1.5 to 5. So that would correspond to a SWR of 3. Okay, makes sense. And if I take the orange line here and do the same thing, and I didn't have time to do the correlate back to the reflection coefficient numbers, but you can see them printed out here. Reflection coefficient of zero point 0.5 would correspond to an SWR 3, and excuse me, and then the reflection coefficient of 0.75. Well, let's see what that is. Okay, you get 1.75 divided by 0.25. Okay, so that's going to probably be something around 5 or 6 for SWR, and that would correspond to a reflection coefficient of 0.75. Okay, now for rho, or reflection coefficient equal to 1, that's 100% reflection, you'll get a maximum of 2 volts, okay, and a minimum of 0 volts. So you take 2 divided by 0. Anybody want to venture a guess what 2 divided by 0 might be in terms of the number? Well, it's infinity. Anything you divide by zero would be infinity, correct? So now you get an SWR of infinity, which is down here. So that's how this goes. So if you were to actually measure the voltages on your line, you would get these kinds of curves depending on what the SWR is. So if you have a short-circuited or open-circuited line, meaning coax, then you should get these really big changes in voltage. Notice that they happen every half, well, yeah, I guess every half wavelength. You get the difference between the maximum and the minimum, and then you get 0 volts as low as 0 volts at the minimum, and as high as, well, it wouldn't be 2 volts. It would be some large number, which would actually be 2 times the incident voltage. So they're assuming here the incident voltage is 1, and 2 would be the maximum in that case. Okay, it could be 100 volts. You would get a maximum 200 volts and a minimum of 0 volts. That would be the case where you have the extremes of either a short circuit or open circuit termination. And things in between, this is what the patterns will look like. So you get things that look more like sine waves, and then if you were to do the actual measurements, but then you would be able to actually, from the voltage minimum and maximum, you can calculate the SWR, which is simply the ratio between the maximum and minimum. And then you can get, if you wanted to, a reflection coefficient from that. Okay, so now, all right, so we talked about, say, the voltage. Now let's look at the combination of the voltage and current. Okay, so here, basically this picture here is just showing you what we've been talking about. You've got a generator on one side, you've got your transmission line here, coax, let's say, and you've got some sort of in this case, they show a short circuit. So remember, for short circuit, you're going to get over here, the current goes to 0, but the voltage doubles. Okay, so but there's going to be a reflection, and you're going to set up standing waves. And so if you measure the voltages of these standing waves and the currents of these standing waves, you'll get this kind of a pattern here. So again, you get kind of a sine. The top looks like more of a sine wave. The bottom looks like kind of a cusp, and that's typical for when you get 100% reflection. And then if we went back to the last slide, you could see that situations in between, you're going to get more of a sinusoidal shape standing wave pattern. Okay, but you'll notice that the current maxima and the voltage maxima are actually now separated not by 180 degrees, but by 90 degrees. So you would get your current maxima occurring about 90 degrees from the voltage maximum, and the same thing with the minimum down here. Okay, so that's just sort of more academic, but it's just to show you how these standing waves actually look on your transmission line. So is this dangerous? Well, yeah, it can be, because if you have a lot of voltage, let's say your source is putting out 100 volts. Well, in theory, you should be getting like 200 volts on the line. If you're running really high power, you might get thousands of volts on the line. And that could be the case, where you have especially high impedance point, say at the antenna. And so that voltage, we'll get into the practical side of it, but just think of this. Here you have, okay, forget about the short circuit. Just, whatever the load is. Let me just draw something here. So let's say you've got, a load. So just represent as a resistor. And that's going to have some sort of impedance, which we'll call ZL. Okay, so that could be your antenna as an example, and you're sending power out to the antenna, and it's reflecting power back down the line. Well, where's that power going? Okay, well, first off, there is a reflection that's going to happen also here at the source. So you get okay. First of all, this is the transmission line, which has a characteristic impedance of Z0 or Z naught, as we call it sometimes. But you have a Z source here, which can be a resistive source. So we typically say that that's equal to 50 ohms. So in this Z0, which is the characteristic impedance of the transmission line, oh, sorry, is sorry, that's not what I want. Is 50 ohms as well. I mean, usually. So you got a match here between Z source and Z0. So therefore, you really won't get any reflection initially, anyway, from power leaving the source, going down the transmission line. If you had a mismatch, let me erase this. Hang on one second. Well, let me. Come on, let me choose the eraser. Probably won't let me do that. Yeah. Okay. So I have to. All right. So anyway, hang on, excuse me. Yeah. So power, all your power, because there's no difference in impedance between the transmission line and the source, all the power is going to go out onto the transmission line from the source. Okay. But that's only in the initial instant that you start, putting power out on the transmission line. Because what's going to happen is you'll get power moving down the line here, or I should say voltage and current going this way. And then you're going to, now a ZL is now not equal to Z0. And so you get this condition of, to wait for the wheel of death to go away here. Anyway, if ZL is not equal to Z naught, in other words, it's something other than 50 ohms, you're going to get reflected power. Oh, come on. And therefore, you're going to get power going backwards on the generator here. Okay. So what's happening? Well, where's that power going? It's going right back into the generator. So it's going to add current and increase the voltage beyond what they're supposed to be, or what the the circuit is trying to put out. Okay. And if this thing would stop, oh boy. Well, let's see if I can at least move on to the next slide. Well, anyway, so we may have some problems from that. We may have an overload of the final amplifier transistors, let's say, or tubes, and they could burn out because now you're pumping in a bunch of current back into this thing. However, there's also an impedance transformation that goes from ZL down the transmission line, and it's going to have at the input of the line here, you will not get ZS equal 50 ohms anymore. You're going to get some input impedance, which sadly enough I can't access yet. I may have to stop the slide presentation for just a second to get rid of this. Oh, I think I think my whole system's locked up. Oh, dang it. I think it is. I can't, it won't respond to the keyboard. Oh well, I'll have to wing it. Sorry, guys. Anyway, okay, so let's just continue on here. I'll just give just a hand waving type of lecture. Okay, so you're going to get impedance transformation down the line. Okay, if this line is anything other than a wavelength, half a wavelength, or multiples of half a wavelength, the impedance ZL will be kind of reflected back down the line here, and depending on the length of this line, it will turn into some other input impedance. Whereas the initial input impedance is ZS here, which is 50 ohms, it won't be 50 ohms anymore. And that's after the very first reflection that will occur. So now you're going to get a whole different impedance. So what does that mean? It means A, that inside the interior of the transmitter, it's got a 50 ohm, it's expecting to see 50 ohms, and it's not, okay? It's seeing something different. So it's going to reflect power internally from say the coax connector on your transmitter back into the final transistors or tubes. Okay, so that's going to happen internally. Secondly, you're not only going to get that current to go into the transmitter, but you're going to get a bounce over here. You're going to get current, or not just current, but power, voltage and current to return back towards the antenna now. Okay. So what does that mean? Well, that means that if I'm putting out 100 watts over here and I'm reflecting back, say, 25 watts, let's say I have an SWR of 3. Okay, the reflection coefficient is 0.5, but that's for voltage or current. If I multiply, you recall that power is the product of voltage times current, correct? So if I multiply the reflection coefficient times the for voltage times the reflection coefficient for current. They're both zero point 0.5. So 0.5 times times zero point 0.5 is 0.25. That would be the power reflection coefficient. Okay, so that means I'm reflecting 25% of my power back if I have an SWR3. Let's just say we got an SWR3 over here because this ZL is 3 times Z naught. Okay, so now I'm getting 25% of my power reflected back. And the transmitter is trying to put out 100 watts as well. So what's happening? Well, guess what? Some of the power is leaking back into the, into the transmitter, maybe wreaking havoc, maybe not. But a lot of that power is going to get added to the power going out of the transmitter, and it's going to all flow back towards the antenna. Okay, so that means I got 25 watts coming down, 100 watts coming out of the transmitter. Now I'm going to have 125 watts going back to the antenna. Okay, isn't that strange? But that is actually what's happening. The the power kind of adds to itself, or adds to the say the output power of the transmitter, and it's flowing back up at 125 watts. So it's actually greater. The power going up the line is actually greater than what's being put out of the transmitter. However, it's 25% is being reflected back all the time. So you can take 25% of that 125 watts, and you actually should get back 100 watts. So at the load, we're hopefully going to get 100 watts going in to the load here, which is our antenna. So you're pumping back 25 watts of that power, and it's not quite 100, but it's a little bit less. But you're getting most of that power actually going onto the antenna. Okay, assuming there are no losses. But of course, there's going to be losses. So you get less than that. But we'll talk about that in a sec. And unfortunately, I can't advance the slide presentation because I had all that information, but nothing's working here. So I have to apologize again. Okay, so all right. So you get that. So you actually, when you get reflections, you will actually get reflected power adding that's coming back down the line here. And it's a reverse wave. And now it's adding to the forward wave that's coming right out onto the line here. Okay. So assuming that all that 100 watts gets out onto the line, it adds to the 25 watts that's just been reflected back from the antenna, and it's 125 watts are coming back up. Actually, I was wrong on the numbers. It's going to be different, and I don't have my slides in front of me to confirm what I'm going to say, so I won't give you the numbers directly. But anyway, so that's what's going on here. So you see that you're constantly reflecting back a portion of that power, but actually greater than the output power of your transmitter is actually going up the transmission line back to the antenna. Now, I'm talking about a lossless system. That means there's no losses on the transmission line. And we don't care about what's going on the antenna. There could be losses there, but all we care about is getting that power into the antenna. And whatever the antenna does with it, it's kind of like the antenna's issue. And that's a whole separate discussion. So I won't talk about that, but I will talk about the losses on the transmission line here. So what's going on with a lossy line? Okay, we have lossless versus lossy. Okay, to remind you, a lossy line is going to be basically a line that has resistance or some sort of dissipative factor going on that will create heat. So some of the power is going to be turned into heat as it travels either back up, or I should say up the line, or back the line, or back and forth. It doesn't matter. Every time the energy is going up, it's going to encounter some sort of resistance. And when it goes back down, it encounters the same resistance. So that resistance will turn some of that power into heat. And so you get dissipation from the line itself. And many of you have heard these kinds of stories where if you have a very high lossy line with a lot of SWR, you will get a lot of heat generated. And the SWR will actually add to the loss. So the higher the SWR, the more the loss you can get on your line. So we're talking about all lines have some sort of loss. And one of my slides does have a loss curve on it, but we can't get to those slides, so we're going to have to just imagine that you have some coax, some coax types have very high loss, and other coax types have lower loss. And loss is a frequency-dependent phenomenon. It increases with frequency. So when you choose coax, you have to kind of choose your coax kind of judiciously. Get probably a lot more, spend more money, get lower loss coax, and go get coax that has low loss at the frequencies you're interested in using it at. Okay, which I won't go into. Mike's gone into that kind of stuff in the past, and um, I, I won't talk about that practical stuff. But anyway, so basically, you may have, let's say, half a dB of loss, okay, on your line, or maybe somewhere between half a dB and 1 dB of loss on this line. Okay, for say per it's RG8, or RG8U or something like that, and it has, I don't know, gosh, I had a good example on one of my slides, but let me see if I can remember. So it'll have probably about half a dB per, oh, 200 feet, something to that effect. Okay, so half a dB doesn't sound like much, but what does it actually mean? Um, 1 dB loss is 20% loss already. Half a dB is roughly 11%. So that's, it's not nothing. You just lost between 10 and say 20% of your power just on the line itself if you've got that kind of length. Okay, length of RG8, about roughly 200 feet long. You'll get about 10% loss, even if you have a totally matched system where ZL is equal to Z naught and you don't get any reflections, you don't get any SWR. Okay, you'll already lose that much power just going down the line. So you'll generate some heat on this line. So that means some of your power is going to be dissipated, about maybe 20% of your power, or 10% of your power will be dissipated as heat without a mismatch. But if you do have a mismatch, that's the number's going to go up. So let's say we've got a mismatch where we get an SWR of 3. Well, you're going to get about 20% loss on this particular line. Again, it's probably about 175 to 200 feet long, RG8, and so you're just going to lose about 20% of your power getting from the transmitter out to the antenna. And then whatever losses occur on the antenna will even increase that even further. Okay. So, however, you will get lost, but, and unfortunately we can't see the slide, but I just want to say in hand waving manner that is that bad? Okay. You're going to get 80% loss just from the transmission line itself if it's matched. Okay. We call that a matched loss. But if it's an unmatched loss, it'll increase slightly. Okay. Let's say it'll go up to about, okay, somewhere between 10 and 20%. You might get, say, 15% as opposed to 10% if you've got a relatively high SWR. Is that bad, really? Okay, think about that. Yeah, we can't see my slides that show all the numbers, but suffice it to say that actually no, it's not bad at all because it turns out that you'll lose about maybe 6 watts or something like that. Even with an SWR of 3, you will have 6 less watts going to your antenna than if you have zero or I should say SWR of 1, which SWR of 1 again is no SWR, no standing waves. So it's a perfectly matched system. You will get only 5 watts more going into your antenna in that situation than if you have an SWR of 3. All right, so that sounds like nothing, correct? And it is nothing, really. So everybody worries about how much SWR they've got on their transmission line, on their coax, when in reality, as long as you're not going really high in SWR, and you're using some sort of matching device or maybe an antenna tuner, which would be the antenna tuner would be over here in between your source and the actual coax that leads out to the antenna. So it would only all it would serve to do would be to tell the transmitter it's hooked into some 50 ohm load, whereas on the other side of the tuner, you've got whatever the SWR or sorry, whatever the impedance mismatch is going on this line. The tuner has to deal with that, but the transmitter only sees 50 ohms that it's connected to. So it's, and the only reason why we're happy there is for 2 reasons. A, we're not having reflected power go into our transmitter, possibly damaging it. And secondly, because manufacturers know that could happen, they add what they call a fold back circuit into your transceiver which allows the power to drop if the SWR goes above a certain level. Usually that certain level is about 3. Okay, SWR 3, sometimes 2. The fullback circuit will kick in and it will reduce the power. So that therefore the reflected power getting back into the say final amplifier transistors is going to be within tolerances. They do expect some reflected power to get back into the transistors, but that they design the circuit such that as long as that reflected power is not above a certain level, it's okay. It won't damage the transistor. But if that reflected power goes above that level, it can damage the transistor. So therefore, they put these fullback circuits in. So the power will automatically be reduced if the internal SWR meter inside your rig detects a SWR of 3 or greater, usually. Sometimes 2 or greater, it depends. But okay, assuming okay, that's why we use the say the antenna tuner. So we always try to present a 50 ohm load to our transmitter, regardless of what the impedance mismatches are on the rest of the antenna system. So therefore, if you're using you know, if you do have a bad mismatch and you do have high SWR along the line here, how bad can it be before it's really going to be detrimental to your signal? Because our goal is to get as much power from say from the source into the load and along that transmission line. And there's something called the maximum power transfer theorem, I should say. But I'm not going to talk about that. But just suffice to say that you want to get, if you've got a matched system, you will get maximum power transfer from, say, the source into the load. If you have a mismatch, you'll get less than the maximum power transferred. Okay, so that's another reason why we like to do that. We would like to match ZL to Z naught, but most of the time we can't ever do that. Usually, almost always, ZL is going to be different from Z naught. So we can't do much about it up here, but we can do something about it down here with an antenna tuner. However, since we can't do anything about it on the antenna end, we're going to get SWR on our line. Unless we're working with a really resonant antenna, on the frequency of interest that we're transmitting on, that we won't have to worry so much about high SWR. But if we're really off the resonance of the antenna, we will get a big impedance mismatch, which would create a large SWR on the line. And then therefore, how bad can we tolerate the high SWR? Okay, so what I'm trying to say is, even if you've got a mismatch where you get SWR of 3, which means you've got, say, 3, different ratio between ZL and Z0 is 3, meaning, let's say ZL is 3 times the impedance of Z0, or something to that effect, or it could be 3 times less too. You can still get almost all your power radiated out without very much loss. And what does that mean in terms of who's receiving your signal? Okay, well, let's talk about S units. S units on the receiving end. One S unit, to remind you, is approximately 4 times increment. Every time your S meter goes up an S unit, the power level has gone up 4 times of the received signal. Okay, so the 1 S unit, is essentially equal to a 6 dB power level change or a 4x, power level change of 4 times. So that's a 300% increase in power. Okay, 300%. Now, if I'm talking about if I have SWR over here on my if I have a impedance mismatch of 3 to 1 here, which would give me an SWR of 3, essentially, and I'm only losing maybe 5 or 6 watts out of almost 100. So effectively, I've lost maybe 5% of my power, or maybe a little bit more than that. In a high SWR, say SWR 3 situation versus a match situation, which the match situation alone is going to make me lose about maybe 10 to 20% of my power anyway. On the receiving end, if one S unit is a 300% change in power, what do you think a 5% loss of power is going to look like on the S meter of that receiver? Do you think you'll be able to see that? No, you won't. So effectively, there's really no difference that's discernible on the receiving end. I don't care how far away the station is. It's, the power level is going to be whatever it is. But if you compare, if you transmit your signal with a SWR of 3 versus an SWR of 1, there's going to be no change effectively in the power that's being received at the other end, no matter where it is. So all that worry about, getting a one-to-one SWR from your antenna onto the line is really for nothing because even high SWR levels aren't going to really do anything. Even if you go up to SWR of 5 or 6 or even 10 sometimes, there really won't be that big of a change. What may happen is you will burn up a lot of the power. Well, you'll burn up more power on your line because the higher the SWR, again, the more loss that the SWR actually adds to the loss. So, but I'm taking all that into account. So even with an SWR of 10, which would give you a lot of loss, it would appear that most of the power is not even being reflected out, or I should say radiated out, but actually reflected and burnt up. Yeah, there is that case. But I have to say that even in some commercial broadcast situations, I've read where the SWR on their transmission line is going to be as high as 50 to 1. Okay, 50 to 1 SWR. Can you imagine? However, the line that they're using is not coax. Okay, it turns out coax is a pretty lossy transmission line. They're using something called open wire line in a case like that, where you've got basically two wires in parallel as the feed line, separated by those spacers that are made out of some sort of wood or ceramic, usually, or sometimes even a plastic. And you can make your own open wire line to be any impedance you want. But the advantage of that is there's almost no loss on those lines because air is the dielectric in that case, and usually because of the geometry, there's very little loss. So they have, compared to coax, practically zero loss. So they can tolerate very high SWR, which on a coax would probably burn up the coax, literally catch it on fire, or at least melt it. Versus this kind of the open wire line, which has very low loss, therefore it's not going to generate much heat. And even with SWRs as high as 50 to 1, they can actually get their signal out because it's being reflected, but it's not being burnt up by loss. Loss again is resistance or something related to resistance, and resistance means heat. Okay, but if you have very, very low loss, very low resistance, you're not going to get much heat. So the power will bounce back and forth, but eventually all get radiated out. Okay, so I think that's as far as I want to go with this. I really apologize again for the breakdown of the slide presentation, not being able to shift it. But as you can see, I still have my little color wheel of death there. So I'm gonna have to reboot this computer anyway after this meeting's over. But anyway, that's pretty much it. The message I want to talk about at SWR. So I'll open up the floor to questions. Anybody want to ask any questions or have any comments?
Thanks, Scott.
Okay.
Very informative.
Yeah, there's an article written by a guy named Maxwell. What was his name? Oh, see, I can't even get out of the slide presentation to see my notes here. W2DU. You guys have heard that call sign before, perhaps? Um, gosh, I don't have my other computer. Anyway, so it's an article. It's called Reflections. It's just titled Reflections, and it was written in the I think in the 80s, and I think they published a series in QST magazine back then. It was I think a four-part series, and so he was an expert. He's a silent key, of course, but he was an expert in transmission line theory and all these kinds of things related to antennas and transmission lines. And so he wrote this article all about this stuff, and he was trying to squash all these myths about SWR. And the big thing back then, as it is today, is everybody thinks you need an SWR of 1 for everything to work right, and that's not true. You do want to match your impedance at the transmitter for sure, but you don't if you don't have a good match on your transmission line because the antenna is not resonant at the frequency you're operating at, and you get other way different impedance at the antenna impedance than you expect, then you're going to get a big mismatch. You're going to get a lot of SWR. And I'm trying to point out that, and he pointed this out, so it's not just me. he was trying to say that it's not that bad. You know, you can tolerate pretty high SWR and still be able to operate but the prudent thing to do in a case like that is to choose low loss transmission line. So you want to work with LMR 400. Um, you want to work with maybe RG213. You know, these kinds of coaxes are really low loss in comparison. You know, the best, of course, would be open wire or window line, but those are not practical. You know, if you're doing POTA or something, or at your house, you're probably not going to be able to do that. So if you're going to choose coax, choose a low loss as possible line, especially if you've got a long run of coax, because the longer the run, the more the loss there is. And so if you're going to have 100 feet or a couple hundred feet, you definitely want to use very low loss coax for that purpose. So you can, if you do have high SWR, you can tolerate that. You know, and if we're running 100 watts, we don't really have to worry about really, really high voltages on our line because, again, you know, typically a 100-watt system, the voltage you're delivering out of your transmitter at 100 watts, if it's a 50 ohm system, is usually about 70 volts. Okay, you're putting out maybe about an amp of current maximum at the current maximum, and about 70 or 72 volts, something like that, at the voltage maximum. So that's what's coming out of your transmitter. So if you even if you have a short circuit or open circuit on the other end of your coax, the maximum voltage you're going to get is about 150 volts. Okay, so you know that coming back down the line, sure, could that damage your transistors? Maybe. Um, you know that kind of thing can happen, and that's why you want to have a antenna tuner. So the antenna tuner can make it look like the you know on the input of the tuner is 50 ohms. So the transmitter thinks it's driving the stuff into 50 ohm load. And then on the output side of the tuner, of course, it's going to be a different impedance because it has to match or do a conjugate match to the impedance that it sees on the input to the coax. So, but that's going to be very different usually than 50 ohms. So anyway, that's it in a nutshell, folks. So again, anybody have any questions on that or anything I talked about? Okay. So bottom line, low loss coax and a good tuner. And then don't worry so much about your SWR. If you, especially for multi-band antennas and things like that, you could get away with quite a bit of a mismatch and still get your power out. Okay. As long as you're not using something like RG58, which will burn up everything because it's extremely high loss coax. Okay. So I'll give the floor back to you, Anthony, and take it from there.
All right. Thank you, Scott. Uh,
Sure.
Great
Oh,
presentation, and
yeah. Oh, yeah. Oh, great. It worked enough. Oh, good. Okay, good, 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 good. Yeah, I can't get rid of this. I saw the presentation at least, right? So you can't see that
yep,
anymore. Okay,
yep.
okay, okay.
Uh, yeah. So thank you very much.
Sure.
And it looks like the next meeting will be on October 20th. Uh, so yeah, uh, hopefully everybody can make it out to Swaptoberfest and enjoy that. And we'll catch you in a month. Uh, so like with that, have a good night, all.
Hey,
Take
Scott,
care.
that was a great job
Good night.
proceeding after your computer flaked out on you.
I
Good one.
know. Yeah, I'm gonna have to reboot this thing. It just had a hiccup, and that's the end of that. But thanks for that. All right, guys. You guys have a good night.
All right. Good
Take
night.
care. Take care. Bye.